Good morning, sir.
Morning. Yes. So, I hope you already studied definite integrals. Now, I haven't posted uh, uh, video on all this uh, integration by substitution, but I will be posting it later. But it was supposed to be um, for this synchronous study. Now, um, for today, instead of discussing integration by substitution, be reserved for asking. I will be going straight ahead to definite integrals. Okay, and this topic actually ties differential calculus and integral calculus. And while differential calculus starts with the time problem, integral calculus starts with the area problem. Then later on, we will see that integration and differentiation are inverse operations or processes. So let's start with the area problem. Mathematicians of the 17th or 18th century, I think, or yeah, 17th century, the 1800s, or well, not sure if Isaac Newton was born in the 1800s or 1700s, but it were the 1700s, yes, that would have been 18th century. Now, they were interested at that time when there was not, calculus wasn't that formally systematized yet, right? And all that was taught in the academy was algebra. They were interested in solving the area problem, where you are given a curve and you want to find the area under the curve, like in the figure here. You have a function y equals f of x, okay, and you want the area under the curve above the x-axis from A to B. That is the interval AB. So the shaded region S there, here. Now, to find the area of a curved region is not as easy as, say, polygon whose sides are line segments. Well, it is easy to find the area or understand the concept of area of, let's say, a rectangle, where you simply measure the dimensions, the length and the width of the rectangle, and multiply the dimensions to get the area of the rectangle. Nothing so difficult or hard about that. We studied this way back in elementary, grade 1, I think. Oh, no, forgot. But then we proceeded to finding area of triangles, okay, where we thought of triangles as simply half rectangles or half parallelograms, right? And the area would just be half. That we can uh, compute the area of a triangle if we know the base and the height. We simply multiply that the two, and then since it's half a parallelogram of a rectangle, we divide it by 2. And then for polygons in general, we can actually also calculate the area by dividing it into several regions, like in the figure there for a 5-sided polygons pentagon, where each region is actually a triangle and whose area we know. But when it comes to shaded out regions with curved sides, how do we measure the area? Well, for circles, of course, we already know how to get the area, but it wasn't that easy back then. I forgot when was the first formula that was derived for pi, and where pi was actually one of the interests in numerical analysis, where the greater the number of decimal places, then that would be sort of the new record for the most decimal approximations for pi. Okay, but then how do you measure the area of a circle actually, right? Now, some sort of a derivation looks like this, where you simply cut the circle into several strips and then aligning those strips so as they form a triangle. So if you look at this circle here with radius r, okay, and then what you do is cut the circle along this line here and sort of spread it out, right, or stretch it so as to make it linear, then you will be forming a figure that looks something like this, which is actually some sort of a triangle that has like several blocks to it. But actually, if you try to make those strips thinner and thinner in the limit, you will actually be forming a triangle whose height is r and whose base is pi r. Okay. Well, r comes from the fact that this strip here or this uh, cutting here has the length of the radius of the circle. And then this 2 pi r here, which serves as the base of the triangle, is actually this portion here, this circumference here. And we already know the circumference of a circle as 2 pi times its radius. So you will be forming a triangle with height r and base 2 pi r. And if we use the formula for the area of a triangle, it's 1/2 base times height. And then there, they were able to derive that the area of a circle must be pi r squared. And here actually, here in here is actually a what they call a crude form of calculus, which uses approximation to get or calculate quantities, and then you make the approximations better until in the limit you get the exact value of the quantity. So again, recall that way back in differential calculus, we started by approximating the slope of the tangent line by using, if you still remember, secant lines. And then what did we do to the secant lines? We let those secant lines approach the position of the tangent line itself so that in the limit, we get the exact slope of the tangent itself. So I won't be going into detail, okay? Because we've already done that regarding tangent lines. And we got the derivative eventually. And then the process of differentiation. So now here, okay, we will be starting with the area problem. And I will just quickly give you an idea of how to estimate the area under curve, and then how to generalize this, or how to arrive at the exact value by using the concept of limits again, and then eventually arrive at a process or way of actually computing the area under curves without having to use estimation and limit, as similar to what we did for, remember, the derivative, where we simply had to use formula. So let's start with this problem, say a very basic one, where you consider a parabola y equals x squared, and you look at the region below the parabola just from the uh, over the interval from 0 to 1. Let me just show the figure. So here's y equals x squared, and you have the region from 0 to 1 above the x-axis. You want to find the area under the curve. How do you do that? We can approximate the area first by dividing, say, the region into 4 subintervals. That is, the interval from 0 to 1 is divided into 4 subintervals, thus having these intervals from 0 to 1/4, 1/4 to 1/2, 1/2, 3/4, and then 3/4, 1. And then what you do is construct rectangles that will sort of approximate the area of the region. Either it will overestimate it or it will underestimate it. And how do you form these rectangles? You can begin by choosing a point on each of those intervals, and then erecting a rectangle whose height is the function value of that point. Or To make it simpler, we can choose the left and say right endpoint. So let me illustrate this. You pick the right endpoints, 1/4, 1/2, 3/4, and then 1. And then you construct rectangles whose height is the function value of those points, right? Which are already given by those vertical line segments there, so that your uh, rectangles will look like this. Okay, you use those as heights of your rectangles, and then you compute the area of those rectangles to estimate, actually overestimate the area under the curve. So it will look something like this. So you have it there. We use the right endpoints, and then we compute the areas of each of those rectangles and sum them up. So how do we do that? Base times height. So each rectangle has a base of 1/4, right? Because we divided the interval from 0 to 1 into 4 equal sub-intervals. So each has a base or length of 1/4. And then to compute the height of each rectangle, we use the function y equals x squared, okay, to determine the height of each of those rectangles. So what is the height of the first rectangle? So if you look at this rectangle here, the base is 1/4. The height is the function value at 1/4. And the function is so simple, so you can just square, because f of x is x squared. So the height of the rectangle is just 1/16. Okay. And then you compute the area by multiplying the base of that rectangle, which is 1/4, okay, and the height of that rectangle, which is 1/16. Okay. So the area of that rectangle would be 1/4 times 1/16, or 1/64 square unit. And then you do it for each of the rectangles. So for example, consider the second rectangle there. Its base is 1/4. And what is its height? Anyone? What is its height? Using the function. Height is, this is 1/2. So the height is f of 1/2, right? Yes, 1/16. Or sorry, 1/2 is squared. Okay. So that would be 1/4. Yeah, you already gave the area. So 1/4 times 1/4, that would be 1/16. Of course, it should be greater than the previous rectangle. So 1/64 and then 1/16. And then you do it for all of the rectangles. So you will have the following. Let me just show. Here, we have the same bases for each of those rectangles. And we have here the heights of those rectangles. We have 1/4 square, because of the height because of 1/4 for the height f of 1/4, then 1/2 squared, because again f of x is x squared. Then you have 3/4 squared, that would be the height of the third rectangle, and then 1 squared, the height of the fourth rectangle. So that if you total, you get 0.4685. And that overestimates the area under the curve. Now we just labeled it for, just to explain why we labeled it R4, because there are 4 rectangles and we use the right endpoint. The right endpoint. Okay, 1/4, 1/2, 3/4, and then 1. Of course, we can also use the left endpoints, so that our rectangles will look like this. The endpoints, the left endpoints are 0 for this course interval. Then we have 1/4 for the next, 1/2, and then 3/4, and then we construct rectangles with those heights. So 0 height for the first rectangle, this height for the next rectangle, this one for the next, this one for the next, so that the sum of the areas underestimates the area under the curve. Okay, and then using the, because we won't be doing this actually here So we usually do it before pandemic, but things are getting easier and easier and easier these days. So let me just skip this part and just show you the computation. So we get for the rectangles previously shown, the area, the sum of their areas is 0.21875, and as stated, they the number there underestimates the area under the curve. So that the actual area lies between these two values. Okay, so we say that the area now of that shaded region, the one under the curve, is between 0.22 and 0.47. Okay, now we can make the approximations better by increasing the number of rectangles, as I shall show. There, same region, but more rectangles. Thus, these rectangles actually have smaller bases. And notice that the error in computation is less because of the smaller widths of the rectangles. Right? And if we compute, we will get, okay, this is like your R8, 8 rectangles, and then the right endpoints as shown in the figure already. R8 will be, you can check this, 0.398 something. And then L8, if you use the underestimate, okay, and so on. Compute the sum up those areas to get this value, so that we know we have a better estimation now that the area is between those two values. And then we do this again. We increase the number of rectangles, and you will see right away that for say 10 rectangles, the error will be less. And then for 30 rectangles, compare 10 rectangles with 30 rectangles, you see that the error is much, much smaller for the case of 30 rectangles. I hope you at least we won't do computations like this here, but at least you know the idea behind the calculation of areas under curves, that we are using rectangles and then we're increasing it, the number of rectangles, so as to make our approximation better each time. And then to get the actual area, what do we do? Anyone? What should we do? Like what we did for tangent lines, right? We let the what they call this, the h approach 0, and then each time we get a better approximation, and then we just observe where are the values going to, and then once we have that idea, we say that is the actual slope of the value. So what do we do here for areas to get the exact area? We start with small number. Yes, we let the number of rectangles approach infinity. So let me just show for more. So that's for 30, but for 50, see, the underestimate, which is this one, and the overestimate are much, much better. That's for 50 alone. And let me just show you a table of values up to 1,000. So here, n represents the number of rectangles used. Here's for left endpoints, and here's for right endpoints. And you see that the approximations are getting better and better each time. You just observe what's happening to the values for the left and right endpoints. So you see that for 1,000 rectangles, our approximation now tells us that it's between 0.33 something and another 33 something. So that it's maybe safe to say that the actual value is 1/3, right? The actual area under the curve, the parabola, is 1/3 square units using this table and our keen observation. But of course, compute 1,000 rectangles, right, by hand, or with just a calculator would take a long process. But actually, using algebra, remember doon sa secant, sa tangent, sa halip na mag-table of values tayo, gumamit tayo ng limits. So we can use limits to construct a formula and then let the n approach infinity in order to calculate the limit itself. Now, I won't be going into much detail here, but all right there, approximately that. And as said, it's 1/3 actually, exactly. So what we do is, let me just show you right away. Evaluate a limit, which is actually the sum of the areas of n rectangles. And then we let n approach infinity, okay, as shown in the figure here. Actually, we can choose any point, not just the left-hand points. We can choose any point in between those intervals and construct rectangles with those heights. Won't matter as long as n approaches infinity. So that by just showing you at least that integrals or areas are evaluated by limit, not by tables. So that we have, okay, to make this long discussion short, we have the following definition of definite integrals, which serve to calculate areas under curves using limit. So you see here, okay, we have the sum of the areas of the rectangle, right? Each rectangle, for example, this typical one, its height is at x sub I star. But anyway, let me just quickly just explain what those quantities mean. And its base is this one, which is denoted by delta x, the width of each rectangle. So that here in the formula, you just have the sum of the areas of the rectangles we were talking about a while ago, and then again, we increase the number of rectangles. So these are sum of areas. And then let n approach infinity, we call that the definite integral of f from a to b. And we give this as the notation for the definite integral of f from a to b. Similar to indefinite integrals where we do not have the subscripts and the superscripts there. Remember, this means the indefinite integral. It's a family of antiderivatives. If you attended the live session, the synchronous one, or at least watch the video. But this is not the same as this. This is a definite integral. Well, we called it definite because we have definite values to sort of consider the function and then evaluate the integral itself, as I will explain later. But never mind this, because this is not a formal calculus course. This is not a calculus course for math majors or science majors. So we will skip this part now and just giving you a rough idea of how we do things in math and why these things are not really intuitive, but rather very formal and analytical. So now we will go to, since this is part of our syllabus, the FTC, or the Fundamental Theorem of Calculus. The Fundamental Theorem of Calculus allows us to evaluate definite integrals rather very quickly. Like with slopes of tangent lines, we just use the differentiation process without having to use a table of values or evaluate a very complicated limit. Okay? So what does the fundamental theorem of calculus say? It says that by looking at this one here, the definite integral of the function f from a to b can be evaluated by using an antiderivative, and then you evaluate the antiderivative at the lower and upper limits, okay, and subtract. Okay, so here in the definition, take note that the function capital F is any antiderivative of the small function f, or small f. Now, this may seem a little bit technical or formal, but let me just illustrate how this definition works in order to calculate definite integral. So let's go back to the area. What was our estimate? 1/3, right? By observing the table with n equals 1,000. So we will show how to arrive at that same value without table of values and without using limit. So what we will do is consider any antiderivative of x squared. Can you give me an antiderivative of x squared? Anyone? Remember, the opposite of derivatives, yes, x cubed over 3. Why x cubed over 3? Because if you differentiate x cubed over 3, you will get, if you bring down, subtract 1, you get x squared. Any antiderivative. In fact, there are infinitely many antiderivatives. So, in the language, or yes, in the language of indefinite integrals, we say that x squared dx, x cubed over 3 plus c. If you differentiate this one, it will still be 3x squared, and the derivative of any constant is 0. It's a family of antiderivatives. So let's just use one without the c. So let me use x cubed. So this is my antiderivative capital F. And we're integrating, or we're considering the area from 0 to 1. So that will be using the notation, the definite integral from 0 to 1 of x squared. And then we will evaluate f of 1 minus capital F, f of 0, using any antiderivative, sorry, x cubed over theta. Okay, so we will have 1 cube over 3 minus 0 cube over 3, and we get 1/3. That quick, without any table of values. It will take a lot of time to use or do in order to just find out a fair idea of what the actual area under the curve is. So to see this more, let's have another illustration. So can you tell me what that means? Well, of course, using the notation a while ago for the definition, this is the definite integral from 0 to 1 of the function x. Okay? Now, if we will use the fundamental theorem of calculus, FTC, to evaluate this, we just consider any antiderivative of x. Can you give me an antiderivative? X. X squared over 2. Right? We discussed that. So you evaluate, or you use the antiderivative instead of using capital F. Let me just give it here directly as x squared over 2. And to remind us that we are integrating from 0 to 1, I put them right here. 0, 1. That means I will be substituting 1 first, and then 0, and then I will be subtracting. So I will have 1 squared, substituting 1 over 2, and then substituting 0, 0 squared over 2 minus. And I get 1/2. So the definite integral from 0 to 1 of x is 1/2. Now let us give this a geometric interpretation. This is area under the curve. What is the integrand? X, right? Now that's f of x equals x, or simply y equals x. What is the graph of y equals x? This is linear, right? Can you describe to me what the graph of this one is? Yes, it goes through the origin. It's a straight line, makes 45 degrees with the axis, right? So if we will draw, let me just show the figure. I wasn't able to show it right. Anyway, so here's quickly the graph of y equals x, right? And we're considering the area under the curve. In this case, the function is a line, or the graph is a line. So from 0 to 1. And the region would be what kind of a polygon? It's a triangle, right? whose area we know how to compute base times height divided by 2. Can you tell me what the base of this triangle is? Obviously, right? Because it's from 0 to 1, its base is 1. And because y equals x, its height is also 1, right? And to compute, we just multiply base times height divided by 2. We get the same result of 1/2 found by merely interpreting this one as area under the curve or the line y equals. But using the fundamental theorem of calculus, of course, we computed it another way and found that they just give us the same result. Okay, so the FTC work. Well, this is mathematics. Mathematics is always precise. So with that, we can use the FTC to compute the area under the cosine curve. Sorry, cosine x. From 0 to pi over 2. Let me show you the graph. So that's y equals cosine x. You don't have to really restudy the graphs of trigonometric functions. But we are interested in finding the area of this from 0, sorry, to pi over 2. Although there it's already given as 1, but let's show that indeed the area under that or that region as an area of 1 square unit. Okay, so let's use the FTC. By the FTC, the area, which is the definite integral from 0 to 1 of cosine x, will be an antiderivative, which is what? Ano yung antiderivative ng cosine? Pag dinifferentiate mo siya, si cosine siya, di ba? Is one, antiderivative ni cosine, baka nakalimutan nyo na. Oh yes, positive sign na. Kasi ang derivative ni sine, si cosine. So si sine ay antiderivative naman ni cosine. So sine x, and then we plug in 0 and 1. 1 first, the upper limit first. So that would be sine, pi over 2. 0 to 1 to yan. Pi over 2 ah. So sine pi over 2 minus sine 0. And if you use your calculator or just look at the angles, pi over 2 and 0, ito ano to 0, 1, okay. So yung ito 1, 0. So yung sine niya yung y coordinate, di ba? So magiging 1 minus 0. 1 unit. So any questions so far? And as discussed yesterday, we will try to discuss just for 1 hour every Tuesday and Thursday. We will just have our synchronous sessions, TTH. Then the rest would be for asynchronous. Okay. So let's this one. I want you to compute the first draw the curve. Very simple lang naman yan. Gamit na lang kayo ng point by point plotting. Plot the curve or yes, sketch the curve. And then I want you to shade the region that is being asked here. And then you use the fundamental theorem to compute the exact area under the curve, y equals x. Just perhaps 3 or most 5 minutes kaya. All right. So what's the answer? Minus value 4. There's the region. So fundamental theorem of calculus, integral from 0 to 2, skip the 4 over 4, 0 to 2. Not always 0 below, by the way, right? 2 to the 4 minus 0. 4 squared. Okay, so that means for the asynchronous sessions, you will be studying the uh, differentiation techniques or integration techniques. Okay, because not all functions that we will encounter here are as simple as that. So please study the technique of integration by substitution. It's very important. And then we will just see how things will go and what things need to be discussed in our next synchronous session on Thursday. Right? That's it for today.
Thank you, sir.
Thank you, sir.